afternoon. We're coming to you live from NASA's John C. Stennis Space Center in South Mississippi, where today a team of NASA and Aerojet Rocketdyne engineers are getting ready to test a RS-25 rocket engine for NASA's Space Launch System program. The Space Launch System is NASA's new heavy lift rocket we are building to send astronauts in the Orion spacecraft farther than they've ever been before in space. When completed, 2 5-segment solid rocket boosters and 4 upgraded RS-25 engines will power SLS to space and enable astronauts to begin their journey to explore destinations far into the solar system, including an asteroid placed into orbit around the moon and ultimately on to Mars. I'm NASA Public Affairs Officer Kim Henry, and today's test is set for 4 p.m. Central, 5 p.m. Eastern. So far, the countdown is progressing normally. We'll have full coverage of today's test, including a reaction from our engine manager following the test. You can follow along on social media with @NASA and @NASA_SLS on Twitter, NASA SLS on Facebook, or using the hashtags #SLSFiredUp or #JourneyToMars. I'm joined today by Gary Benton, who is the Chief of the Project Management Branch of the Engineering and Test Directorate here at Stennis Space Center. Gary not only has a rich history here at Stennis Space Center, but also with the RS-25 engine. The RS-25 engine was formerly known as the Space Shuttle main engine, and there are 16 engines in inventory that will be upgrading for the Space Launch System. Gary, can you tell us a little bit about today's test and how long it'll last?
Sure, Kim. Today's test is supposed to go for 535 seconds full duration. That's just under 9 minutes. Some of the objectives we're testing out today is this engine has a new controller. The controller is the brain of the engine, and we've got some updated software, and we want to run this controller through all the paces and verify everything works, just like it will for flight. Another important objective is to simulate the conditions that the engine will see when it's pre-flight, like on the launch pad. It's important that we get the liquid hydrogen and liquid oxygen propellants at the right pressures and temperatures and the same bleed flow rates and such. So we're simulating the vehicle conditions pre-test and during the test. Some of the other things we'll do during today's test is we'll run the engine into different power levels.
Well, we're certainly looking forward to the test. We're less than 30 minutes away from test activation, and of course, safety of our people and our engine are our top priority. There's always a possibility of delay, and as we make sure conditions are correct for the test. We're also excited to be joined today by NASA Edge. They are here for their first rocket engine test. I hear they've got a great view of the A1 test stand. How's it going, guys?
Hey, thanks, Kim. We're very excited to be here at Stennis Space Center, and right behind us is a live shot of the A1 test stand. Now, the SLS, we're gearing up for that eventual rocket test down the road, but we're very excited here today, and Blair, in 30 minutes or less, we're going to be witnessing our very first RS-25 engine test.
It's certainly a day of first, Chris, and I got to tell you, it's the first time that we, as NASA Edge, have been to Stennis Space Center. It's the first time for NASA Edge to cover a rocket engine test. It's also the first time I really understood why Kim wanted to be in the confines of a control center and not outside, because this is profound heat. But yeah. The real important story, though, is that we're happy to be here because we're actually joining NASA on this journey to Mars, and that's significant.
Yeah, this is a first for here. The RS-25 engine will be the engine that's going to lift SLS into space. And coming up in a few minutes, we're going to be talking to Todd May, who's the SLS program manager. But first, we got to figure out where Franklin's at.
Rumor has it that Franklin has somehow secured himself quite the position on the 7th level of the A2 test stand. Franklin, is that true? And tell us about the view.
Guys, I am on the 7th level of the A2 test stand, and the view here is spectacular.
How's the temperature? What's the temperature like up there, Franklin?
Well, the temperature actually is pretty good. There's a nice wind blowing up here, and I actually have a fan in front of me because I have these 1K lights, production lights on me, so it actually feels pretty good.
I tell you what, looking at that view, looking at the monitor with the A1 in the background, how high up are you?
Guys, I'm on the 7th level. I think I'm more than maybe 100 feet off the ground. It's pretty high, but it feels good.
So you ready for the test today?
Well, guys, as we were talking about the view, I believe I have the primo viewing location to see the test this afternoon. And for the record, as you've already said, this is my first time to Stennis, and this will be my first engine test. Now, Chris and Blair, you guys had an opportunity to cover a solid booster test in Promontory, Utah a couple of years ago, but today marks the first time that we'll be together as NASA Edge to cover this test. Now, I have the same feeling I had in my body the first time I saw a rocket launch. I'm very excited about it. What about you guys?
Well, I tell you, Franklin, we're very excited as well. And I got to tell you, we're here with Todd May, the program manager for SLS. Now, you've probably gone through, I don't know, hundreds of tests and launches and things like that. But here today, you're about to witness another. Tell us what you're thinking right now.
Well, Blair, this is a really big day for human space flight. We're going to take the engines that are going to take humans out into deep space again, and we're going to run it, hopefully a full mission duration, over 500 seconds with a brand new state-of-the-art controller. And it's going to be a big day. I think we're all going to enjoy it.
Now, Todd, it's been over 2 years since you've been with us on our show. And for those viewers who are tuning in for the first time and really don't know what SLS is about, explain to them about the Space Launch System.
Okay. So the Space Launch System is an exploration class launch vehicle. It's meant to carry the Orion capsule and humans out into deep space, out beyond the moon, and eventually someday to Mars.
You know, Todd, back when we had you on the show before, you mentioned a great analogy between the Apollo rockets, the Saturn V and the SLS, and you compared it to a Stingray. Can you tell us a little bit more about that comparison?
You mean the car, the Corvette? Oh, sure, I did. Well, you know, if you look at the shape of a Corvette today, and it's not a lot different than you see the lines. It looks very similar to one you might have seen 40 years ago, but inside of that machine, it's a lot more efficient. It is faster, it is stronger, it is safer. I think of SLS in much the same way. You could stand back and say, well, all rockets are kind of shaped the same because they have to go fast and they're pointy on the top and they have engines on the bottom. But the SLS is really designed to be state-of-the-art.
Awesome.
Hey, no, Todd, you know, some people say, you know, we have launch vehicles in inventory that can take crew and cargo into space. Why do we need such a heavy lift vehicle like the Space Launch System?
Well, that's a good question. So the other rockets we're talking about today are being designed to take crew and cargo to the International Space Station, which is about 300 miles from Earth at any given time. And that gets you to a certain place in space. It gets you to a stable orbit around Earth. But if you want to go into deep space, it takes a lot more energy. The other aspect of it is when you go into deep space missions, especially if you're going to go on to asteroids or Mars, deep into the solar system, those missions take years. And if you're going to take humans out there, we're pretty needy organisms. We need our food, our water, and things like that. And so all those things you need have to get up into a place where you can take them into deep space. And so you need a pretty big rocket to be able to do that.
You need a lot of water today.
That's right.
You know, one of the things I'm wondering, I know that NASA does a good job of using sort of their existing technology and building on it. So what have you taken from the shuttle program? But then what are you improving on the shuttle program as well through these?
Sure. Well, we're taking some of the best parts. These engines are some of the most efficient and reliable engines in the world. And we have 16 of them in our inventories, and they have actually flown humans in space before, so we know they're good engines. We took the boosters from the shuttle, and we said, we want 25% more power. We stuck another segment on it, and so now we have 5-segment boosters. The core is actually a new state-of-the-art design. We decided to improve on that by using things like self-reaction friction stir welding. That's a big phrase, but basically,
and awesome.
But yeah, it is kind of an awesome process. The machine that does the welding, the large one, is over 200 feet tall, but it's very efficient. It doesn't take a lot of people to actually build the tanks themselves. So we've reduced the cost. We've made it more efficiently. We've used state-of-the-art electronics and have upgraded it to be ready for the next generation.
I'm sold. This is great.
Hey, as we continue with our journey to Mars, is it fair to say, Todd, that NASA is using a 3-prong approach where we're looking at Orion, which is our next generation spacecraft, SLS, and the ground support?
Yes, I actually think of it as 3 programs, but 3 prongs makes sense.
NASA prongs. That's it.
NASA prong. There's actually 3 major programs. The Orion program, they develop the capsule. They get the crew ready to go. That capsule goes on the rocket. The ground system has the Launch Control Center, what's called the VAB, where we actually put all the pieces of the rocket together. They have the mobile launcher, which goes out to the launch pad, and then they perform all of the launch. Once it clears the tower, it goes to Mission Control in Houston, and we have an operational mission. So it takes all those pieces to be able to pull this off.
Well, this is fantastic, Todd. Thanks so much. We actually have a short video that actually takes us through those 3 prong/programs. Let's check it out.
Hey, welcome back. We're live at Stennis Space Center as we prepare for the RS-25 engine test. I tell you what, boy, I'm getting excited already because that was a very cool video.
It was a cool video, and it was actually awesome for us this week to actually drive around Stennis, meet some of the people that work here, and see that a lot goes on down here. It's a really important place. In fact, it's been said that everything that goes to space comes through Stennis Space Center.
That's right. Since it's our first time here at Stennis Space Center as a team, we decided to just kind of check out the place, talk to some folks, learn about the heritage of Stennis Space Center and the A1, A2 test stand. I had a chance to sit down and talk with Paul Foreman of Public Affairs, and so let's check out this pretty cool video.
Paul, it's great to be here for this historic RS-25 test, but Stennis has had a rich history of engine testing, in particular with space travel. How did Stennis get involved in the engine testing business?
Well, back during the 1960s, when President Kennedy made the announcement that we were going to go to the moon and return the men safely in this decade, they needed a place to test the really large engines and stages for the Apollo program. Stennis Space Center, being geographically located on the Pearl River and near the Gulf of Mexico, provided several of the things that were needed to test those engines and stages. It was very sparsely populated. Like I said, it was on the Pearl River, which connected to the Gulf of Mexico, so they could transport those stages down to Kennedy Space Center to integrate into the Saturn V for the Apollo program. In addition, because I said it was sparsely populated, we had to relocate 5 small towns to make way for Stennis, but that gave us the ability to test those really, really large engines for the Apollo program here at Stennis.
Now, you're still using the test stands from the Apollo in all the testing that you're doing today. What are those test stands, and how are they being used in this new technology that we're developing?
You're absolutely correct. The test stands that we're using for the RS-25 test today was used during the Apollo program for testing the upper stage of the Saturn V. That test stand was converted during the 70s after the Apollo program ended for testing the space shuttle main engine for the shuttle program. And now we've converted it again for testing the RS-25 for the Space Launch System. So it's had a rich history from the very beginning and still being used today.
I understand a lot of reconfiguration goes into the test stands when you're testing a new engine. But what did you have to do to prepare the stand to handle the RS-25 for SLS?
Well, even though this is the same engine that was used during the shuttle program, we needed a different thrust adapter and different mechanism to gather the data that we need to get for testing the RS-25. So in addition to reconfiguring it for accommodating the engine, we had to reconfigure it for gathering the data that we needed for testing this new engine.
Considering just how many engines have been tested and how Stennis has helped NASA during the whole space exploration and spaceflight program, how do you see Stennis continuing to help NASA as they take their journey to Mars?
Stennis, because we have 13,800 acres where the test stands are located, surrounded by a 125,000 acre buffer zone, gives us the capability to test really large engines and really large stages to get us off the ground and into deep space. So Stennis will always be here ready to test those really large rocket engines.
Mr. Walt Janowski, who is the RS-25 program manager from Aerojet Rocketdyne. Walt, just how powerful is the RS-25 engine?
But you're going to see this engine go from 0 to 500,000 pounds of thrust in a little under 5 seconds, and then continue at that thrust level for the next 8.5 minutes.
Now, the RS-25 was used on the space shuttle. What's going to be different on the Space Launch System?
Well, on space launch, the geometry of the vehicle is different. So we're going to explore all the different inlet conditions that results feeding the engine. So we're testing to make sure that any condition we see on SLS will first experience on the ground. In addition, we're upgrading all the electronics. The old controller on the SSV was extremely reliable, but it was vintage, the old Apple Mac era of semiconductors. So we're upgrading it. No more dial-up for us. We're going 4G all the way.
Now, how long has Aerojet Rocketdyne been working with the RS-25?
We got the contract originally in the 1970s, early 1970s, and we flew for the first time in 1981. And since then, we've continually tried to upgrade. The agency's invested in newer and newer models of the engine, and it's been a tremendously reliable engine for them. 135 successful flights. We've got over 1 million seconds of experience in flight and on the ground.
Now, in the early 70s, this engine is just as old as I am.
That's right.
Now, what makes the RS-25 engine so unique?
When NASA chose this engine design for the space shuttle, they chose a very high state-of-the-art geometry and engine cycle. The laws of physics haven't changed. It's still one of the best, most reliable engine cycles, the most highest performing engine cycles on the planet. And all we need to do is update the electronics to today's standards, and it's good to go.
Now, the RS-25, when it was used on the space shuttle, it was a reusable engine. Now, after these engines are all used up on the SLS, you'll be moving to an expendable engine. Will that save money?
That's right. We have got lots of ideas to reduce the cost, to increase the affordability of this engine. And we're looking forward to building another generation of engines that can continue to fly this vehicle into the future.
Well, Walt, thank you so much for being on the show today. We look forward to the test in about 10 minutes. Guys, back to you.
Thanks so much, Franklin. It's really great to hear from Walt and just all this great information we're getting on this test. And I tell you, despite the heat radiating from my forehead, this is one of the most exciting events I've been to in a long time. Despite the action you're seeing out at the pad right now, the test has not started, but it will start soon. And we're actually joining NASA on this journey to Mars. I know I've said it before, but I'm very excited about it.
I tell you what, we've had a lot of milestones over the past year, dating back to last December with the first successful flight test for Orion, the Exploration Flight Test 1, to the qualification motor test in Promontory, Utah, and to the series of RS-25 hot fire tests we've had here at Stennis, including the test here today.
Right here.
Because as we're testing these RS-25 engines, that will culminate into what we call the green run test.
Yeah, and you had an opportunity to sit down with Trevor Martin, who actually is working on the B2 test. Let's check it out.
As we get ready for this RS-25 engine test today, let's kind of jump ahead a year or two down the road, because I understand that this is leading up to a bigger test called the green run test. Tell us a little bit about that.
The green run test will be the first time that the fully integrated SLS core stage and the 4 SSMEs or RS-25s will actually be integrated in hot fire tests.
All 4 together, not just one test, one engine that we're seeing today.
All 4 in the same flight profile and time duration that it will be at Kennedy, which is about 550 seconds or so.
Now, you're going to be doing it at the B2 test stand.
Correct.
Now, why wouldn't you conduct at the A1 or at other test stands? Is that a specific test stand for the test?
Yes, it is. Historically, that test stand was the test stand created for testing fully integrated stages. It started with the Saturn V first stage. We moved on to the main propulsion test article for Space Shuttle. Shortly thereafter, we did the Common Booster Core test there, and now we are going to do the Green Run test at B2 for SLS.
Now, I see there's a lot of construction going on, so are you renovating the whole facility for that test?
Just the B2 side.
Okay.
The B1 side is still a single engine test stand, but the B2 side hadn't been touched more or less for maintenance purposes in about a decade or so.
And how's that process going right now?
Oh, it's going quite well, actually. We started with restoration of the test stand to its original configuration. Then we're going into what we call build out, which is adding more structure to accommodate the increased height for the SLS core stage comparatively to Saturn V or the external fuel tank of the Space Shuttle. And then lastly, we're going to do the actual special test equipment. And those are the physical hookups that are unique and special for the SLS.
And I understand that there's a particular piece, a structure where you actually had to lift it and move it over 20 feet 3 inches?
Yes, sir. So we have what we refer to here locally as the MPTA structure. It was the structure.
And what's that stand for?
Main propulsion test article.
Okay.
And it was erected to actually accommodate the thrust takeout loads of the actual shuttle test article.
Okay.
But since it was a side-mounted vehicle, it was actually erected 20 feet 3 inches to the south side of the building to actually put the 3 SSMEs in the center line of the building to evenly distribute the load. Well, we're going back to an inline vehicle like Saturn, so we had to literally pick it up and move it 20 feet 3 inches to put it in the exact center line of the building.
Now, I'm hearing rumors that you're using dishwasher detergent to actually, liquid detergent to move that structure over. Is that true?
Yeah, you would think it would be a complicated task, and trust me, it was a significant task to actually pick this structure up that weighs well over hundreds of thousands of pounds, all structural steel, and move it 20 feet. So we actually raised all 16 feet, erected rails under the feet, and used a hydraulic system lubricated by dish detergent to actually slide the structure to the north.
So how many times did you put your hands in there to make sure your hands were soft?
It was pretty fun and unique to watch that happen.
I tell you what, the Green Run test is going to be another step closer to the journey to Mars.
Absolutely. As one of our slogans, and it's always been said that Von Braun said, all roads to space lead through Mississippi. So every vehicle that manned vehicle we've ever flown has always come through Stennis Space Center.
Hey, welcome back. We're joined now by Dawn Davis, who is the electrical design lead for the B2 SLS Green Run test. How you doing, Dawn?
Good, nice to see you guys.
Hey, Dawn, I have a question. I understand rocket test and being maybe a rocket engineer. What does an electrical engineer do for a test like this?
Well, we're responsible for all the electrical systems on the test stand. That includes the data acquisition system, control system, video systems, all the ancillary systems like the oral warning and test warning systems. So a lot of stuff we're responsible for.
Sure. Now, Dawn, you're going to be collecting a lot of data for this particular test. How long does it take to collect all that data, to analyze it, to synthesize it, and see if the test went well?
Yeah, you're right. We have hundreds of channels of data on this test and any other engine test that we have. But it actually depends on the type of data that we have that's available for the test. We actually have 2 different data acquisition systems, a low-speed data acquisition system, which actually samples at 250 samples per second, and a high-speed data acquisition system, which samples at higher rates, upwards to 200,000 samples per second. So after a test, 30 minutes after, we can have a subset of that data ready for what we call quick look data review. But we typically have a data review a couple of days after the test.
It's awesome. I mean, clearly you're not only getting a lot of data, that data is essential in future design and future tests. So is it a concern being so close to such hot temperatures and things like that. How do you protect this data under those extreme conditions?
Well, our data acquisition system is actually housed inside the test stand, so it's actually protected, but our sensors that actually collect the data, that's actually the point for the data, we make sure that we acquire sensors that are made to operate in those harsh conditions, make sure that they can withstand cryogenic temperatures, as well as the vibrations that we'll get on the test stand.
I didn't think about the vibration side. I got the temperature side, but that's...
Yeah, man, you have a big engine out there that's going to rumble. When you'll see in a little bit how the ground shakes when that engine shorts. So you imagine anything on the stand is going to vibrate as well.
I'm already shaking.
Well, you know what? We're getting close to test time, so I tell you what, we're going to go back to Kim and Gary, and we're going to get ready for the countdown. Kim, take it away.
All right, thanks, Chris. We're actually less than 6 minutes away from today's 535-second test. That's actually about a 9-minute test. When the SLS is in flight, the engine will operate for about 480 seconds or close to 8 minutes. But Gary, what I really want to know about is, why do we test engines?
We test because we love to hear the shake, rattle, and roll and look at all that awesome power strapped into the test stand. No, but in all seriousness, we test because we want to verify that engine performs as designed. If there's going to be a problem with the engine, we want to catch it on the test stand. We don't want to have a problem during flight that could jeopardize our crew or cargo.
Absolutely. The RS-25 is a liquid-fueled engine. It's liquid oxygen and liquid hydrogen, to be exact. How much liquid oxygen and liquid hydrogen will we use in today's test?
During today's test, we'll burn about 150,000 gallons of liquid hydrogen and 60,000 gallons of liquid oxygen. That's over 200,000 gallons total propellant. That's enough to fill up a 10 of your average size swimming pools.
Wow. Can you tell us a little bit about today, what's happening to get ready for today's test? Maybe what's happening behind the scenes in the test control center, or maybe even what time you all got started today?
Yeah, well, test day usually starts about 6 a.m. There's hundreds of instruments that we're going to be looking at for today's test. Pressures and temperatures, speed probes, strain gauges. So we want to verify that all that instrumentation is working properly before we even get started into test day. And so after all the electrical engineers and technicians have checked out all this key data system, the test conductor will call the group together and have a pre-test briefing in the morning. He'll go over the test procedure, any special operations. It gives a chance to verify all open constraints are closed before test, and gives a chance for anybody to speak up if they have any reasons not to go into test. So shortly after that, the team of technicians and engineers will dispatch. They'll go out to the test facility and get the test stand ready, start to regulate gas pressures that we'll need to support the test. Some folks will go out to the barge docks and get the propellant barges ready in case we need to transfer fuel. Another team will go to the test control center, and they'll start to set up the data and control systems. One of the things that we do after we get the new software loaded onto the engine computer is to power on the engine and go through a series of purge sequences. The reason we do that is because we don't want to have any moisture inside that engine. Remember, these propellants are really, really cold, and we don't want anything to turn into ice or solid in there. So we purge the hydrogen system very well with gaseous helium, because that's the only gas we have that won't turn into a solid at that cold of a temperature. And we purge out the liquid oxygen system with nitrogen. And once all that's
how many
done,
purge sequences do you go through before a test?
There's 3 or 4 purge cycles that we usually run through. After that, we've got the engine preconditioned. It's ready to have some liquid oxygen and liquid hydrogen drop down. So we drain some of the propellants out of the tanks. We open up the facility valves, and we begin to chill the engine down. It takes a couple of hours to get all that metal cold. We've got to get liquid temperatures in that engine. So we do a slow, methodical process. We start with liquid oxygen. Once the temperatures are stable, we'll send the technicians out, do some inspections, make sure everything's working good on the engine, and we repeat that process with the liquid hydrogen system. After that, really, we bring up the water pressure, do some final checks, and send the test crew back to the test control center at a safe distance. Deflector water pressure is increased. The exit ignite torches are activated, and when we get closer inside the 1 minute, maybe where we're at now, the test conductor is doing a final polling of the management team and the test team to verify that everybody's a go for test. We have limited time on our super high-speed video recording systems and data recording systems, so those are usually the last 2 systems that are turned on. So if all the conditions are met, the test conductor will have what's called a prep complete indication on the screen, and at that point in time, he can initiate the auto sequence start and begin the test.
So there's actually a button you push. Is it a red button?
Well, no, it's like it's a green button.
Okay.
There's a red button, but that's in case there's an emergency shutdown, and we don't ever want to hit the red button.
Absolutely. Well, we're kind of in standby right now, waiting for the 1-minute notification for the RS-25 test. Today's test will be 535 seconds. And it sounds like we did get the 1-minute notification. So, Gary, maybe what happened just right now in this time, right here before the test?
Well, yes, they are probably just finishing that bleed sequence. Like we said earlier, we've got to get those inlet temperatures and pressures just right. So they're probably fine-tuning the control valves to make sure we've got the right temperatures, conditions at the engine inlet and inside the engine, and also getting the tank pressure set.
Standing by for the RS-25 engine test here at Stennis Space Center. Sounds like auto sequence has started. 135-second test of the RS-25 engine has concluded. That certainly was exciting. You could actually feel the power from it. Gary, I'm curious, what's happening right now immediately following the test, and ultimately, what do you have to do to get ready for that next test?
Well, wow, there's probably a few people in the control center high-fiving because that was a very, very successful test, and you got to see an awesome display of the power. And can you imagine 4 of those RS-25s all going at the same time? But yeah, so what'll happen right now is the engine will go into some post-test shutdown mode, and we'll do some securing of the facility systems. We'll evacuate the propellants out and get the stand in a safe condition. And then shortly thereafter, we'll dispatch some engineers and technicians out there to do final inspections of the test stand. And tonight, the engine engineers will go out there and do some inspections on the engines. We'll turn on some drying purges and let those purges run overnight and get the engine all dried out after test. And another thing is people will start looking at the data. You know, we've got, like I said, all those hundreds of measurements. So engineers will be poring over the data from today's test to look and see if all the objectives were met.
And that's the part you guys really like.
That's right. Lots of plots and graphs and numbers for the engineers to look at. And usually what happens is a couple of days later, we'll have a full-blown formal data review, and we'll talk about the objectives and start planning the next test. If we didn't meet an objective into today's test, we can roll it over into the next test. And so that's kind of the process that we go through there.
Yeah. Well, your engineers and technicians certainly did a great job today. It was a great show. We're going to go back out to NASA Edge to get a reaction from the crowd out there. It looked like a whole lot of steam.
I tell you what, Kim, I'm speechless right now because, you know, we've seen shuttle launches. We've seen launches at Vandenberg, from Kennedy, from Wallops. I tell you what, this was unlike anything I've seen before.
And you know, Kim, to me, the most amazing thing is most of the time when you see a launch, the spacecraft is moving away from you. And here you feel like you feel the impact sustained. And that must be what it's like for the astronauts. And I know because of my wife and other intellectual deficiencies, I'll never be an astronaut, but this is as close as you can come to feeling what they feel on a launch. It's pretty impressive.
It was just sheer raw power for 8.5 minutes. I mean, just to see all that steam coming out and the crowd with the excitement taking video and pictures, and they're all fighting for jockeying positions to get that ultimate picture.
My chest cavity was kind of rumbling.
It was unbelievable.
Absolutely.
And Franklin, over there in the A2 test stand, I can only imagine what it was like from your end.
It was a beautiful sight, guys. The power, as you said, you could feel it from all the way over here, and you were just a little bit closer than we were, so I know you could definitely feel it. And after the test was over, actually was over here viewing it with Walt Janowski from Aerojet Rocketdyne. He smiled and he was happy with the results, so I assume it was a very successful test. Guys, back to you.
Now, Franklin, because joining us now is Steve Wofford, who is the SLS Engines Manager. And Steve, what are the initial results?
Initial results are great. We ran full duration, 535 seconds. We met our test objectives. Didn't note any anomalies at this time, so now we get the fun part of going through the data.
Well, that's awesome. I tell you, and you can feel the excitement here with the crowd. And I mean, already here, you feel instant victory. You know, it's total success. But tell us, you get the data. How long before you actually know that the data, with the data that you get, that the test has been a success?
Okay, so we know that the test has been pretty successful right now. So we had one of our primary test objectives today was to demonstrate the 4.5-minute chill cycle on the fuel side, which is a flight-like condition for SLS. We hit that, we made that, so I'm really, really happy about that. It's a very much shorter chill cycle than we had in shuttle, so we knew the engine could do it, but we demonstrated it today. So the other test objectives, we know we were successful. We'll spend a week going through the data to make sure there's no other anomalies that we've missed.
Now, on a test like this, I think you probably just answered my question. Are you going to use this data on today's test for the next development test?
Absolutely. So we learn every time we go. So we'll take the lessons learned and the data from this test, fold them into the test objectives for next time.
And I just got one final question. Steve, you're out here, you see the crowd. I mean, we're on our journey to Mars. You see the crowd all pumped up. What was your feeling like?
My feeling was elation, just like you guys, right? It's a great day for NASA. It's a great day for the SLS program. It's a great day for our Liquid Engines office and Aerojet Rocketdyne team. So it's good to be here.
So it's a great day all around. I mean, apart from intense temperatures, which the engine did a far greater job of handling temperature than we ever will. It's just an awesome success, and we're just glad to be a part of it.
I tell you what, Kim and Gary, we had a success from our end. I'm sure you had a great time viewing it from your end. Take it back. It's back to you.
All right. so much. Today's test of the SLS RS-25 engine is a major milestone on our journey back into space and on to Mars. It's been a pleasure here watching the test with Gary Benton to get this insider's look of what goes on behind the test scenes. We want to thank you for joining us today for our live coverage of the Space Launch System RS-25 engine test here at NASA's John C. Stennis Space Center in South Mississippi. We'll now conclude today's broadcast. To follow the progress of NASA's Space Launch System, you can follow us on Twitter at NASA_SLS and Facebook.com/NASA SLS, or visit us on the web at www.nasa.gov/SLS. And for all the latest news from NASA as we reach for new heights to reveal the unknown for the benefit of all humanity, visit www.nasa.gov.